invite our first speaker, Dr. Ramanan Lakshminarayanan, who is a Chief Technical Officer at Sajanan Medical Technology. He's an engineer from IIT Madras, a design expert, an operation expert, quality in Six Sigma, quality champion, inventor, renowned subject matter expert, quality jurist, and a successful entrepreneur. I think I am not even 10%. He has made it possible to convert design to fulfill unmet needs, making affordable. A highly decorated with awards, significant ones being pillars of pride from GE, design challenge champion from HP and Jaguar. He's been instrumental in development of mobile and dental X-ray products, raised consultancy services, provided support and knowledge building to leaders across industry segments, specifically to leaders in medical device industry like Medtronic and Philips in India. It's a privilege to have you, sir, and may I request you to please enlighten the audience with your talk.
Thank you, Dr. Sanjeev. Thank you. It is nice to have the good words from you. It's a pleasure to be on this platform. And what I thought is, let me put across the thought process in terms of the strength. What are we talking about? That is one of the example. I thought I will take it from here to, as a case study. So that we will be aware and we will be able to see what are we talking about. Before I jump onto my presentation and talk about this, I would like to stand here on the slide to talk about the SMT's legacy. The topic today, met and unmet needs. In 1990s, when India was not talking about affordable healthcare or make in India, they were all not slangs. Dr. Dheeraj Lal sowed a seed looking at the pains of a common man. He is an engineer by himself, electrical electronics engineer, and a specialist in building the laser machines. So what he brought from the laser, the world's best machine, what he was making it across, or the diamonds to cut. The stents is a metallic tube. When I'm cutting diamonds, why not I cut the metal tube? That is what is the thought process in 1990s, where he sowed the seed and nurtured it. Today we have grown with multiple centers across the globe, and we are saving lives across the globe. Where he thought we will save people in India, now today we are saving people across the globe. That is the history what we are talking. And we will see what is the story behind this, how we are making it across. That is the DNA each one of us carry on that platform. Before, what we talk about this, onto the stent, I have worked on Dr. Khurana was talking about, in India, we need to make some of the, products out of India, the diagnostics equipments like that. The GE's Innova cath lab is the cath lab which is used in the hospitals for stenting, in which I had an opportunity to work for 10 years when I was in GE. I hold few patents on that. This is the machine which is used for stenting. When we talk about this machine is being used for stenting, you are seeing a slant table on which the patient is lying, and the catheter goes from the left of the picture. If you see that it is going from the groin, where there will be an incision, when the entire catheter goes to the artery, when the heart itself is pumping the blood for the entire part of their body, but that has got some bifurcations which are covered. The heart muscles are being covered by the artery. When the artery gets a block, like in this picture, then it will not be able to supply the blood to the muscles. And the muscles are not receiving the oxygenated blood, then the muscles start dying. That is what is exactly the part of heart attack. So when the catheter is being sent inside, doctor doesn't know where the catheter is and how it goes. You see onto the cath lab screen, there is a monitor. That is the only option what is available to him to see where the stent is. So one side, the MNCs like GE, Philips, Siemens, many of them make the cath lab that is outside the body, like Dr. Sanjeev was talking during the initial part, outside the body and inside the body. from Shajanand, we are talking about the product which is inside the body. What is the challenge? The challenge onto the stent, if you look at the stent as a whole system, it has got, like a long 1.5 meter of a length, a fragile tube with which that is stainless steel, of course, is a material, and also with polymer, and it carries the stent at the end of it. We mark that as a balloon, like that is where the stent is getting carried. The stent by itself is a tube on which the design has to be played in order that you have to crimp that on that. That is how it is being carried. The stent, if you look at that, once it is being deployed into the artery, as I have shown during the last slide, where it is being expanded at the clogged position to keep the flow going, what is happening is, like onto that stent, we need to carry also the drug, which is to be placed for a period of time so that the healing happens. You see that the drug, the picture below that gives you an idea of how the drug is being coated onto that. That is, the thickness of that is 4 to 6 microns. What are we talking about? 4 to 6 micron of the drug, which is being coated onto the stent. That is a technology. And we, the SMT as a company, we are the first guys who brought the biodegradable polymer in drug coating to the world. And the stent itself is a structure. And all of them, both of them has got the challenges in reaching the tortuous path. Like that is what are we talking about. And, like I'm moving to the next slide, which talks about the flexibility of the stent. In this, I have captured 2 images. One is the shepherd crook origin, where I have placed that screen. You see onto the bottom of it, there is no blood flow. You are seeing only the small traces of the lines, but there is no blood flow. And that is where the block comes in. So when the doctor sees that, that is what is the location where I need to go and stent it, what doctor is going to do is he is going to take the catheter all the way in, and he has to reach that spot. And once he has reached that spot, and then there is a, he expands the balloon, and the stent is being placed at that location. Then he takes across the catheter route. The stent stays there. That is the metallic tube. So here the trick of the trade comes in. The metallic tube which is being taken, and it has to have the metal which is essentially needed when it is being expanded. The stent should stay there. It should not collapse because of the pressure of the artery itself. And there is also a pulsating blood pressure. Like we all know 80, 120 is the blood pressure. And the blood pressure operates. That is what is the fatigue loading, what are we talking about. If the stent, which is the design, which is you are seeing on the screen, as a tube, the leftover material on the stent is about close to 12 to 13%. Now you are seeing the stent is being expanded, and this is how it is being placed over. And it is not in a straight artery. Like the arterial locations can be longer in length. So you may have to have different sizes in terms of it. So what the doctors at sometimes need to do is they have to overlap 2 different stents. And, like one stent, maybe 32 millimeters, another plate area is 8 millimeters. That is the combination which he makes. Though we make the stent for the comforts of the doctors from 8 millimeters to 48 millimeter in length, and to the arterial size of 2 millimeter in diameter to 4.5 millimeter in diameter. That's what we make. He chooses the length combination. That's where the overlapping comes in. The regulatory authorities also look at, in terms of the fatigue, which I talked about because of the blood pressure, you are seeing the rows in the screen. I'm animating it back. It again talks about how much is the complexity. The first stent is being placed, the second stent is being placed, and you are seeing in the shepherd, that is the type of curvature where it goes and lies. And it has to sustain. It should not break because of any of the loads. If there is a breakages, then the artery will get punctured, and there will be a blood leak. That's not a cost what we want to have. So regulatory authorities look for what is the worst scenario, which you will be predicting from the computer models. So this entire part of it, like if you look at this part, this is another one where, now you see the catheter is going. The catheter from the growing, which we have talked about it, this is the end of it where the stent is being carried on to that. The catheter goes all the way through the various tortuous path of the artery from the bottom to the heart of it. It claims the doctor sends at that location. The moment it reaches the targeted location of the diseased vessel, and he expands. That is how the delivery system as a whole also plays a role. It comprises of the components like stainless steel tube, polymeric tube, and the balloon which is being carried over, on which acts as a carrier to carry the stent, and that's how it goes across. This is the stent has to be more having a stronger support irrespective of the material has been removed. And if you look at this, we also have the test drives. Most of us are cars, like we know that before the car is being released into the market, they have the test tracks. In the case of a test track or a test drive which is being made for a car, the driver sits on the wheels and he is driving it. But in the case of the stent which is being placed over, the driving end is 1.5 meters away, and we are driving it from the bottom of it, and it is blindfolded. The doctor is seeing only the screen. From here, you will see the road, the curvatures, everything you will see. But whereas it is to be driven all the way through. You are seeing onto that, manning over onto that is the technology in terms of this entire stent portion, the delivery system has been done in Shahjahan through computer-aided simulations, through digital. Today, the world is talking about digital. We made the stent, the delivery system, everything from the digital format. We had the first-in-class design. Today, we are talking about the stent. What we are made is the benchmark in the world. You can see the many competitors, and I have put the brand names and the manufacturers of that. There are various manufacturers, Ultimaster, Rsiro, Xian, Sierra, say for example, in the case of Xian, that is from Ambat, and Resolute, Onyx is from Medtronic, the Synergy is from Boston Scientific. You see on all this, the force that is required by driving this entire part is what is the lowest part that is being consumed by the brand, which is delivered to the market today as Superflex screws. And this is the brand, what are we talking today, is making waves in Germany. The product which is made from Surat, a portion in the corner of India, we are treating the people in Germany, France, across all the European countries. We are placing it in UK, and that is how the stent is making. It has established by itself, because of its quality, the comforts with which the doctor can go into completely occluded artery. We call it as CTO part, which is completely occluded, where he will not be, that is called as chronic total occlusions, where the stent cannot be, 90% is a block. Where he has to reach first, that is what are we talking about? Even reaching that spot is not difficult. Once he reaches, and he will be able to expand and the life can be saved. So from the time where the Dr. Dheeraj Lal thought about that we will do the stent in India for saving Indians, today we are talking about saving the millions of people across the globe. So the mission and vision is pledged to save millions. How are we achieving it from the research labs? As I have shown you, like as an example, take it across from everything from the digital, convert that first pass design, make the stent, because we cannot go to the market saying that I have the best stent, I will try it on you. Before going up to that, I should be having a complete confidence in terms of what I am delivering. Today, this is the benchmark in terms of the deliverability. That is what we are talking about. I'll be happy to take any questions, Sanjeev.
I didn't know that the stenting is so old, and you said it's early 1990s, and it's pretty good to know. And one more thing got clear today. A lot of people say, doctor ne do stent dal diya. Today I know what these two stents are basically. First time I'm understanding this technical part. Of course, that's the advantage of being a moderator, where you learn in first time.
Nice of you, Dr.
Yeah. Second thing is, do DCGI team really understand these nitty-gritties? What is your experience with them?
Can you come back?
Yeah, I mean, does DCGI team really understand these nitty-gritties? What is the experience with them?
Yeah, because in terms of the explanations into the discussions, we always make them understand in terms of the complexities involved onto that. Okay. They very well, they understand the complexities. we used to have, constant interactions and with them. So I
Right.
trust, in them.
Okay. And could you also enlighten us about the other cardiac medical device from your experience perspective about like pacemakers, defibrillators, valves, how the India is actually doing about those kinds of devices? How do you see the scope and what kind of market percentage we have it here? If there is some idea available, it will be very nice for audience.
Excellent question, Dr. Sanjeev. The next one part, the world, many people have heart valve diseases.
Yeah.
Like what you touched upon about pacemakers,
Yeah.
valve is one of the part people have valve replacement. Today it is not happening. Reason being the cost of valve replacement is close to 30 lakhs and 40 lakhs. India is coming up onto that front in terms of making the valves, which is affordable. Like what are we talking about stents? Like where we will be able to make where, Indian origin valve comes into the market. There are people, who have started thinking about it. We are also in the same directions in terms of bringing out valves. As far as the, pacemakers and other, related products are concerned, they involve the complexities in terms of mechatronics.
Absolutely.
So both electrical and electronics also have to come into the picture.
Yes.
In India, anybody is doing at this point of time, people have not ventured because of the complexities involved onto that part of it. That's where it stands. Probably a few years down the line, people will be able to come up with that. But valves is one of the area India is definitely going in, and we are also having an eye on it, and it is on our research bed.
That's fantastic. And one question before we move on to the next speaker is that, are you doing some backward integration for the materials which you have to use for your products?
The material of the stent?
Yeah, are you doing some backward integration for that?
Yeah, that's a good question, Sanjeev. There are two aspects of it.
Yes.
What we do is, we ourselves is not wanting to do the material manufacturing. Say, for example, the stent manufacturing is concerned, there are different elements. One is the delivery system itself and the stent tube itself. The stent tube extrusion comes from the United States, and we are supporting Indian ecosystems, for the delivery system. For example, the next stent which we have developed for the peripheral artery for the aged people, the entire delivery system is made in India. We have developed, a supplier for us, worked with them, what is the requirements, and, the delivery system manufacturing itself is a different part. And he is supplying from Hyderabad to us. So that is how we are developing the ecosystem. Similarly, another one product which we are developing, which we developed an Ahmedabad-based supplier, and he is supplying manufacturing us. So we are committed to the development of the ecosystem. Who can do? Somebody is doing onto the extrusion of the tubes for that. We will be able to support what is needed, because the technology. But we want to remain corely into the development of the product, like what I talked about the other ends, like unmet needs of valves from India and stuff. That's where our eye is.
Thank you, Dr. Ramanan. It's been very, very good to listen to you, and I'm sure many people would have taken some shots from it. And let's see.
Thank you, Dr. Sanjeev. Thank you so much. Thank you. It's a pleasure opportunity to meet you over here. Thank you. Thank you.